Dave. Thank you, Dave, for introduction and for invitation for giving a talk here. And the topic that I'm going to talk about today is about the continuum modeling of active fluids. This is the work actually primarily done by my PhD student, Hwang, and in collaboration with Rachel Biaron at Liverpool. So given the name of the sea, so let me start actually by introducing some very well known actually collective dynamics of the microstreamers. I think this is probably now the very classic and the most well known, and this is actually the video from O.T. Cruz, and these two actually the suspension that you see are the suspension of Junaliana salina, and the other is a suspension of the Chlamydomonas nivalis. And if you mix the suspensions very well and then leave it for a while, then you will see the famous hexagonal pattern, which is very similar to which you see in thermal convection. And so therefore people have called this bioconvections. And this bioconvection happening in shallow water or shallow liquid the suspension of this the streamers actually swing upwards have been very much studied and well understood over many years. The other thing, other interesting collective dynamics, which you can see also in such a bottom heavy streamers, which is swing upwards, is the Bliss instability. So imagine you have a suspension which flows downward in a pipe, and then what is typically happening here is that those cells actually tend to swim towards the region where the downward actually velocity is the strongest. So in such a situation, what you see here from this video is that the stream actually towards actually the center line here, and then they form nice actually structure plume, which often become unstable to this instability, which is another well-known, relatively well-known actually phenomenon in this type of suspension, and that also have been analyzed by myself and some other people here. And also another famous one, I think this is now too well known for many people. This is a famous movie actually created by the group of Ray Goldstein in Cambridge. So this is actually a little sensor drop of suspension of Bacillus subtilis here, and the closed loop in the near the contact line. You see that the suspension actually create the vortices and jet, the size of which is much greater than actually the cell size, right? If you put the fluorescent bead actually to this the suspension, you see that the beads are actually moving with much larger scale. So all the examples that I have shown today are actually happening order of 1 centimeter scale or 1 millimeter scale. So it's not actually a very large scale problem, but it's very interesting. But clearly, as a fluid dynamicist working on many things in high ranges of flow, so clearly one of my important goal is to actually tackle much larger scale problems, which has actually relevance in environmental science and energy science. So these are the examples where these actually suspensions are important in practice. So you want to actually mitigate predict or this behavior of the harmful algal bloom, which can actually destroy the local coastal area. And also you wanted to harvest actually the biofuel from photobioreactors. This is where the problem size become also big. So clearly the one challenge that I have seen, and since I actually started to study this topic, is that it is actually typical continuum models we're using is very, very expensive to solve, because often it has a very large number of dimensions. Therefore, what we wanted to have is actually an idealistic view is that wanted to have a very low computational cost, but actually it's robust. So actually we want nothing more than like the advection diffusion equation. But actually we also want that model to deal with the semi-dilute regime. So that's our objective. And then I haven't understood this is a hard problem for many years. But actually, today I'm going to present some progress that we have made actually in this year. So let me first start this talk by introducing an early phenomenological model, which was introduced by Hadley and Kessler. So before that, so let me try to actually formulate a problem. I'm going to consider any random flow here, arbitrary flow, in which actually the lots of actually streamers are suspended. Okay, so in this particular talk, I want to consider a gyrotactic streamer, so like the Chlamydomonas or Junaliana or Volvox or Heterosigma like this. So here, what I'm going to do here, this is the axis, the one of the vertical direction, and that will be axis one of the horizontal direction. That is one of the vertical directions, and gravity actually towards actually minus z directions. And this is the equation of motion for the streamer. So I'm going to assume that the streamer actually swim a constant velocity we see in a direction towards in a e direction. So E is actually the orientation vector of the streamer, and then this orientation vector obeys the famous Jeffers equation, which actually is given by this the 1/2 omega cross E term. But as I said, I'm interested in dealing with the bottom heavy the gyrotactic streamer. Therefore, I'm going to add this famous term introduced by Hadley and Kessler. So this is the term which makes the cell always actually try to which make the cell swim upward in the absence of the flow. Also, I'm going to assume that the cell actually experiences randomness in rotational motion because of the biochemical noise actually inside of cells. I'm going to add this to the rotational the random noise in the rotational motion. So the goal is to actually create a continuum model, as I said, which must be more is but at the level of the advection diffusion equation. So before I introduce the model of the Hadley and Kessler, let me just briefly recap the relation between the microscale and macroscale in the earlier days. Okay, so let me briefly recap the famous fluctuation dispersion relation, and the main progress of which were actually made at early 20th century by Einstein and Smoluchowski. So let me consider a Langevin equation, which is described the particle displacement in the presence of the nodes. Here the psi is the delta correlates noise, and I'm going to assume that the strength of the node is square root of 2d. Okay. So the Langevin equation, this equation is now can be easily solved. So you can actually compute the variance of the particle, and then you will see that the variance is proportional to 2 times the t. If t is a time. And then, so what it means actually the strength of the fluctuation actually, not surprisingly, characterize the variance of the particle displacement. But this description can be written in terms of Fokker-Planck equation, which become actually a macroscopic description of possibly many particles or single particle or whatsoever that actually give you the diffusion equation. So here n can be viewed as a PDF of a single particle, but also n can be viewed actually the particle number density in the case you have many particles. So what is nice is that here in this equation is that the D can be computed by evaluating the second order moments here, here. And then D, in this way, we can relate the macroscopic, actually, continuum model with what is happening at microscopic level. So what is important here is that the fluctuation in microscopic level, it becomes actually the diffusion coefficient or dispersion. So therefore, this actual relation actually established the link between the fluctuation at microscopic level and the dispersion or the diffusion in microscopic level. So the early model introduced by the Petit and Kessler actually utilized this rationally very, very well. Okay, this is the bastion diffusion equation they introduced for their model in 1990. So here, here you see that VCEE bracket term is the average streaming velocity that is typically obtained by solving the Fokker-Planck equation, which actually deals with the randomness in the orientation motions. Okay, so the E bracket actually gives you the time, the ensemble average is actually the streaming direction. And then D is actually utilized this expression coming from fluctuation dispersion theorem. And then D is calculated from the variance of the relative displacement from the mean displacement. And then that expression can be converted in terms of the relative velocity VR, and then they use this actual expression to approximate the expression of the diffusivity. So in this description, so what is unknown is tau, which is a correlation time, and typically what they have done is that they actually take the value measured from experiment. But in that experiment, typically they use people use the stationary suspension. So basically, they use the tau from stationary suspension. But tau, I should say that can be a function of actually shear or local vorticity or local strain. So therefore, this model is in fact is supposed to be valid only when flow is stationary or the flow's strength is variable, right? So that was the earliest model, but actually there was another model which was introduced actually and used actually quite popularly for the last decade is called generalized Taylor dispersion theory based model that was actually introduced by the Howard Renner and his coworker is Chuck Frankel. So in their actual theory, they use exactly the same advection diffusion equation. And then they also use exactly the same as the drift caused by the swimming motions. But they actually have very sophisticated form of expression of diffusivity. Not going to explain this at the moment, detail how you derive this, but here, what I wanted to point out that this actual expression is dimensionally proportional to VC squared over dr. So what it means here, in this actually theory, the time scale is actually automatically given by 1 over dr. So there's no need to get the time scale, correlation time scale from experiment. So this is one of the important advantage of this generalized Taylor dispersion theory. Okay. So let me briefly introduce how they actually derive this equation. So to do this, let me go back to the very original work about Taylor aries dispersion theory. This is from the work of G.I. Taylor back in 1950s. He considered the nice experimental apparatus. Here you see that there is a large, very long and thin horizontal pipe, circular pipe, and he applied the liquid flow here through the pipe, and he also put some substance here, and he wants to examine how this substance actually evolve in axial direction. Okay, so what he wanted to do is that using the average concentration over the cross section C bar, he wanted to actually compute the effective diffusivity, which was essentially created by this pool advection diffusion equation is validated throughout the entire pipe. What he observed is that if you put the small, actually the blob of the substance, or and then because of the flow, it forms nice bowl shape of the structure due to the parabolic velocity profile. And then this actually dispersion actually create the extra diffusion in this type of equation. Okay. So 3 years later, the rotophoto aries actually model this thing more accurately. So what he has done is that he considered the full analytic solution of this full diffusion, advection diffusion equation. And then what he has done is that he compute the average concentration with a cross-sectional average, and he calculate the relative displacement by evaluating first order and second order moments of this mean average actually concentration. And then he used actually expression comes from the early the fluctuation dispersion theorem, and he managed to get the effective diffusivity, which compares very well with the research of the G.I. Taylor. And this is here as the Peclet square over 48 is the extra diffusion, phenomenological diffusion caused by this ball-shaped dispersion. And here the Peclet number is defined based on the average velocity and the radius of the pipe and molecular diffusivity. So the core of this theory is that in the theory of aries is that you actually throw away the direction that you don't want you're not interested in. So what you do is that you actually take average those direction, and then you actually get second of the movements along the direction that you are interested in. So this actually iterationally was exactly adopted in this generalized Taylor dispersion theory, which looks much more complicated. But if you look at the rationale behind and of this theory, you will see that they use exactly same thing, same rationale actually developed by the Taylor and aries. So in this theory, what they have done is this. So they consider Smolakowski equation for a single particle in time and space and orientation. And that's a Smolakowski equation. And that the initial condition of this, the psi, which is a PDF of this equation, is actually given by the delta over x, delta over e. So it prescribes the location of particle and orientation of particle. And they also assume that G, which is actually the velocity gradient tensor, local velocity gradient tensor, and they assume that G is constant. And then what they have done is that they wanted to actually convert this Smolakowski equation into this advection diffusion equation. So what they have done is that they actually evaluate the first order and second order moments using the psi, here the PDF coming from Smolakowski equation. And using these, they computed the drift velocity and the phenomenological diffusion coefficient that can be used for this advection diffusion equation. Okay, so all this sophisticated expression comes from the psi. And then actually in the case of the gyrotactic streamers, and Hill and Bees actually shows that this UD is equivalent, is the same as the one that Pedley and Kessler actually used. And this expression was actually a bit complicated, but this is the diffusivity expression they were using. It's right. So these are the kind of outline of generalized Taylor dispersion theory. And then actually there are quite a few studies which actually now show that this GTD theory, generalized Taylor dispersion theory, actually performs much better than Pedley and Kessler model. Okay. So let me consider, to introduce such examples, let me consider following again downflowing suspension of gyrotactic microstreamers. Okay, so So that in the work, here I'm going to introduce the work by the O.T. Cruz and his collaborators, and here what they wanted to do, they wanted to create the actually Taylor aries dispersion model. So this is 1D the bastion diffusion model along the pipeline. So N bar is again the average concentration over the cross sections. So they wanted to calculate the mean drift caused by the gyrotactic particles, and then effective diffusion along the x directions. And then they actually compare, to get this effective diffusion, they use the Padley and Kessler model, here they call FP, and also generalized Taylor dispersion theory. Also, they actually do the DNS by putting lots of actually the individual particle, which is obeying the equation of motion that I introduced. So let me zoom this particular part, and let me draw your attention along for these red curves. You see that the solid curves actually a prediction of the effective diffusivity from GTD, generalized Taylor dispersion theory. And then this the red curves, actually the prediction coming from Padley and Kessler model. And these dots are actually from DNS. What you can clearly see here is that this effective diffusion is actually described much better by this GTD model in comparison to DNS. And then, but the GTD model looks really good, and so we actually adopted this model to analyze actually the flow in a vertical flow in a vertical pipe, and we tried to get the steady solutions in a downflowing vertical pipe. Here's N0 means actually center line side concentration. So, and then if the N0 means 1, that means a uniform suspension. Okay, and then we also couple this direction diffusion equation with the Navier-Stokes equation, and through the buoyancy term, because those cells are not actually neutrally buoyant, and they are heavier than surrounding liquids. So this Richards number indicates average cell number density. So if you increase the Richards number, that means actually you get more dense suspension. So what you see here is that as you increase the Richards number, when flow rate is 0, so you see that there's one new solution coming up, and then you can follow this branch, and then that solution actually still exists if you go to very high Richards number, when you actually compute this solution using Padley and Kessler model. On the other end, if you repeat the same calculation with the GTD model, again, you see the same solution coming out, but actually it becomes actually singular. And so we thought initially, there's something strange happening in GTD model, but we begin to realize that this is probably corrective behavior, and this is actually something to do with the fact that the continuum model that we are using we're not able to describe the dense regime of suspension. Okay. But in any way, so what I wanted to tell you here is that even though GTD model looks correct, but in practice actually creates something nasty which you want to avoid in practice. Okay. The other drawback of the GTD model is that it actually doesn't work in strain dominant flow. So this is an expression of diffusivity, which is a function of B, and you need to get the B to get this diffusivity. Okay. So what is happening here is that this actually B is actually obtained by solving this equation. Okay, and this unstable version of that equation. This right-hand side term is a driving term, which is nothing to do with the stability of this equation. And this term is basically coming from the Fokker-Planck equation operator that was used by Padley and Kessler. So if you get anything correct from Padley and Kessler's actually assuming velocity calculation the PDF, and then this operator should not generate any mathematical problem. But from here, what you can see here is that G can create a problem if the eigenvalue of G has a positive real part. Okay, so by definition of G, which is actually the velocity gradient tensor, so in such a flow is a strain dominant flow. So in this case, you can have a singularity. So therefore, in that case, you can't have the, sometimes you can't have the diffusive the expression of diffusivity. And this was actually shown by the Rachel Biaron here back in 2011. And this is a diffusion, diffusivity, behavior of diffusivity along the strength of the velocity gradient tensor. This is a situation where the diffusion, the velocity gradient tensor is dominated by the vorticity component. You see that everything looks fine, but as you actually goes to the strain dominant, actually the velocity gradient tensor, so you will see that something nasty is happening here. Okay. So clearly, we want to have something better than generalized Taylor dispersion theory. So I was fortunate enough to work with the two people, Hwang and Rachel Biaron, and that's actually, they made actually good progress. Actually, I'm trying to explain what they have done actually together with me. So today I'm going to introduce a new directional diffusion model. So let me start from the Smolny-Koski equations that I briefly introduced for generalized Taylor dispersion theory. But here, I'm not going to assume the constant velocity gradient tensor. I'm going to consider entire flow, whatever in the domain in of interest. Okay. And then, if you integrate this equation in E space once, you will get this equation. The trouble is that you don't know the bracket and E that is coming from the solution to the Smolny-Koski equation. But from the actually work of the Padley and Kessler and GTD models, what we want is this form of the models. Okay, so it still uses the mean drift caused by computed by the calculation of moment in space, but we want to find something extra from that actually something extra from directly from the Smolny-Koski equation. So what Lloyd actually has found is that you can actually express this E bracket in terms of the EPK plus extra term, and after some nasty manipulations, you can actually have exact expression even like this. Okay, so here the first term is actually emerging from this calculation, and that is a Fokker-Planck equation operator used by the Padley and Kessler, and driven by the time derivative of this f. So here n is cell number density, and so that you can decompose this into 2, and you can actually get this f. You just need to feed this information into this equation, and you will get this velocity. And also, you can get the second term from here, which is related to spatial variation of the f and this E bracket. And the last term, you can also get the effective diffusion here in this way. So if you now put all this actually this relation back into the original equation. So before doing that, so let me simplify this Fokker-Planck operator LE, and then I'm gonna actually substitute this relation into the full direction diffusion equation, and you will get this exact expression coming from the Smolny-Koski equation. Okay, so this expression is equivalent to the Smolny-Koski equation. We haven't done anything wrong. We haven't made any approximation so far. And then you can clearly see that to get the V and V Porter T and VC and the effective effect, and we still we still need to know the full Smolny-Koski equation. Okay, so therefore we needed extra magic, and so we did a symptotic analysis by assuming that the swimming velocity is much smaller than the dr times L. Dr is rotational diffusivity, and L is the length scale of the flow. And also we also assume that this velocity, swimming velocity is much smaller than surrounding flow velocity. By doing so, what we can do is that we can actually now express the VC and effective diffusion in terms of this FPK that is actually solution used actually in the Peterlee and Kessler model earlier days. And then we can plug them in here, then we will get this nice expression. So now we don't need to solve the Smolakowski equation. So you only need to solve this equation to get the flow field. So let me briefly compare the difference of this actually new model with the generalized Taylor dispersion theory model. Okay, so let me first consider. So here, before that, this left side is summarizing the formula for the VC and diffusion here, and the right hand side is actually the value of the VC and the diffusion became from generalized Taylor dispersion theory model. So what you can see here is that if we consider first, consider there is no flow here, then what you see here is that all those things goes away and those two models actually become identical. Okay, these two are identical in the absence of any flow. On the other hand, if you consider now uniform shear flow, like the one developed by the original model of the Franker and Brenner or here these and other people, is that you will see that the VC goes away because this FPK is still independent in space, and then this becomes zero, and then these two model seems to be similar, but actually GTD model actually had this extra term, which was the source of the singularity problem. In our case, we don't have that. So as long as this LE operator behaves well, everything's okay, and it's numerically. So let me try to give you now two examples to demonstrate the capability of this new model. So this is the first example. So we're going to consider the downflow here, but it's a periodic in x direction and given by this. Okay, and then we are going to put lots of streamers there, and we first simulate the full Smolakowski equation. This is the advection diffusion equation directly transformed from the Smolakowski equation. Here I'm presenting the simulation results. Okay, so this is the initial distribution of the cell number density, which is uniform in the space. And these are the evolution of each term. So at, sorry, let me just start this again. So at initial instance, when the simulation starts, you will see that this term, this advection term caused by Peterlee and Kessler this equation is exactly balanced with this unsteady term here. And then you will see that this term very quickly diminish, and it forms nice actually the dense region of the suspension. And then this advection term caused by the Peterlee and Kessler the equation actually the balance eventually with the diffusion flux, and the steady state, you will see that this advection flux is exactly balanced with the diffusion flux here, and all these two terms in the end goes to zero. So therefore, in the end, the equation that you're going to have is this for the steady state. Okay, this is the results of the Smolakowski equations, and then we compare these results with the one calculated from generalized Taylor dispersion theory, and the one from our new model, asymptotic, obtained from by applying asymptotics to this model. And you will see that all these actually three or more is similar, and it's very difficult to find the big difference between the three. And then I have to remind you that all three use the same the advection term here, drift term. So therefore, what it means is that this effective diffusion directly coming from the Smolakowski equation is actually similar to the one coming from generalized Taylor dispersion theory and our asymptotic model. Okay, So in this particular case, what is good is that you can actually get the full analytical solution of the Smolny-Korsky equation. Okay, using that solution, you can define the strength of shear dWdx at S, and you can plot the effective diffusion coming from the Smolny-Korsky equation as a function of the shear. And then here you can compare as actually the four diffusion coefficients, okay, directly coming from Smolny-Korsky equation with the Yak transformation. Okay, in the case of the XX components, actually all three are really similar, which actually really demonstrate why the actually generalized Taylor dispersion theory and the small performs so well in comparison to Smolny-Korsky equation. Okay, that also explains why it actually the GTD model works so well in previously. Here, this cross diffusion from DXG, as you can see here, is that the both actually our asymptotic theory and the Smolny-Korsky equation and GTD are all quite different, although they show all similar tendency. But if you look at the DZX here, what you see here is that these guys show very strange behavior. So if you actually define the diffusivity using the definition typically used from the particle, the variance of the particle, the DXG and DZX are supposed to be identical. But remember that in our diffusion coefficient directly obtained from the Smolny-Korsky equation, so therefore there is no reason that they have to be identical. So in fact, our DZX actually become negative here, and they both actually the new model and the Smolny-Korsky equation shows more or less the same behavior. Okay, so the similar thing is happening in this DZZ component. Actually, what you see here is a GTD theory. The DZZ value from GTD theory is largely different from the other two. Okay. So from this observation, we are now really motivated to go for another geometry with hope that it makes huge difference. So what in my last talk, I'm going to consider this final example. Okay. So now what I'm going to consider is this is very the quite famous example now coming from the contribution from McDermott and John Kessler and Roland Stoker back in 2009. Okay, so here is their experimental setup. So this is their small flow chamber. They put the rotating the belt here, and then they make that actually move like this, and by doing so they create the flow. And here you see no slip condition should apply. So therefore, in the middle of the chamber, there is actually a large shear created by this setup. So if you have large shear rate, and what is well known is that this actually shear rate at this location, those streamers actually can form this layer. This is a suspension of heterosigma Casio. It's another gyrotactic streamer, and the excessive shear. Actually, they show that the excessive shear can trap the microalgae, and so the microalgae form this thin layer. Okay, so we actually examined the instability of this layer, the last year, and then we managed to show that it becomes unstable with the Smita, who is now in Liverpool for postdoc. Okay, so the mechanism of this is quite simple. If you have gyrotactic streamers, if you don't have any surrounding shear flow, they only stream upward because of the mechanical feature of the streamers. They swim against gravity. But when you actually have a background vorticity, then the viscous torque applies along that direction, and then this viscous torque and then this gravitational torque are balanced, and it forms a steady state. However, when the background shear is really strong enough, actually now this term begins to dominate over the entire dynamics of this equation. Therefore, the particle needs to rotate with some frequency. So therefore, cell begin to tumble and losing the behavior of swimming upward. Okay, so this is the mechanism. So we considered the situation quite similar to that case. So this is again the same flow geometry. And now we consider gravity is in downward direction. We consider horizontal flow, okay? And in this horizontal flow, we will have a large shear region here. and here, up there and down there. And then we expect that the cell will accumulate along those regions. Okay. So again, we apply we actually we perform the direct numerical simulation of the Small-Minkowski equation. Again, this is the equation coming from the direction diffusion equation directly coming from the Small-Minkowski equation without any approximation. And again, this is the initial distribution of the cell number density over the jet direction. And this is the contribution of each term. And then at the initial instance, similarly to the previous case, this swimming vector term balanced with the unsteady term we see, order t comma jet. And then let me run the simulation. What is happening is that this term, again, similarly to the previous case, goes down quickly to 0. And then now diffusion flux begins to rise slowly with some non-zero velocity that we see here, although this appears to be quite small compared to this one. Okay. And then it takes quite some time to get the steady state, but eventually we reach the steady state. Okay. So in the end, we reach the steady state, but you see that now there's a big difference between here and this here. That is really because of we haven't put any actually the swimming or sedimentation in this direction, which means that actually entire swimming, the cell actually moving along this direction, and this difference actually characterizes the upward shift of the entire cell medium. I just want to remind you that we apply the pediatric boundary condition here. Okay. Okay. So we also consider we get the steady state. Again, we make a comparison. Okay. So now we begin to see that there is a big difference between the exact results and generalized Taylor dispersion theory. Okay. So this yellow line is the results steady solution obtained by applying generalized Taylor dispersion theory. And the blue one is the exact result from Small-Minkowski, and the red is coming from our new model. And you see that now our new model performs much better than actually generalized Taylor dispersion theory. Okay, that behavior actually become even great, more pronounced actually in this case. That is largely because this GTD behave much more worse than our asymptotic approximation. So clearly now our new model, we have shown that our new model actually performs much better than generalized Taylor dispersion theory. So we now hope to use this one for our future study. So maybe let me conclude my talk. Okay. So basically what we have done is that we have actually derived a new form of a bastion diffusion equation based on the local information of the flow. What it means is that if you know the local vorticity or local shear rate or local strain rate, then you can actually solve this, with that you can solve this Fokker-Planck equation locally. And you can actually use this solution to calculate the others, okay, VC and DEF. So basically, by doing so, you don't have to solve the Small-Minkowski equation. You just need to solve this equation, the sum of the extra calculation for each point. But actually, that can be done easily once you actually tabulate actually the solution of the VC and DEF as a function of the local vorticity, for instance, if the cell is spherical. So therefore, it can be much more handy. Although we have derived this equation, I should mention that this D effect, it's not real diffusion. It really does not actually the model's diffusion. Okay, it actually took all the funny thing happening in each space, and then that actually was all actually described by DEF, and that was written in this form. Therefore, we need to know exactly what this DEF actually does in practice. So clearly, what I want to say is that we don't know yet how this DEF has actually linked to with the individual microscopic level dynamics. Okay, so the fact that this guy has a off-diagonal term, which are not symmetric, means that the diffusion, the term, the solution to the Smolny-Forsky equation may generate super diffusion or subdiffusion phenomena, about which we don't have a great idea yet, so we need to explore in the future. So let me conclude my talk here, and thank you for your attention.